The Doppler effect was discovered by Christian Andreas Doppler, a man who was born in a country called Salzburg, which is now Austria, in 1803, and died at the age of 49 in 1853. He was an Austrian mathematician, known and celebrated for his principle of the Doppler effect. The Doppler effect, or Doppler shift, is described as the change in frequency or wavelength of a wave in relation to an observer who was moving relative to the wave source. The reason you all probably know what it is because you have already taken this class, or since a common example of the Doppler effect is when a speedy and loud car passes by you, and the pitch drastically changes from higher to lower. Here's a video demonstrating the Doppler effect in real life. As you can hear, there's a clear change in pitch, starting from higher, then once passing the observer, going lower. Stuff like this happens all the time in today's day and age, but how about in 1842, when it was initially discovered? There weren't exactly quick sounds loud enough going around just to hear it down the street, which makes this discovery that much more impressive. Here is a diagram demonstrating how the Doppler shift works using a car. As you can see, in the direction that the car is traveling, in front of it, there is a higher density of sound waves coming from the car. This is because the waves in front of the car bunch up, almost like the car is catching up to the waves, whereas behind the car, the waves are lagging behind, like they cannot keep up. In this example, person A would hear a noticeably higher frequency and higher pitched sound than that of person B. However, if the car were to pass person A, then they would hear the same pitch. Mathematics with the Doppler shift. The equation of the Doppler effect is defined as frequency observed is equal to the speed of sound plus the velocity of the observer divided by the speed of sound plus or minus the velocity of the source, all multiplied by the actual frequency. The reason it's plus or minus is because it depends on which direction the sound is traveling from relative to the observer. Evidently not left to right, but rather coming towards or away from the observer. Minus if the sound is traveling towards you, and plus if it's going away. Think about it like this. If it's a higher pitched sound, it'll have a higher frequency, and a lower frequency with a lower pitch. In the equation, we are dividing what we are adding or subtracting. Adding something will make it a larger number, which will mean you are dividing a larger number, giving a smaller result, and a lower frequency. And it goes the other way around. Subtracting will give a smaller number, and dividing that will render the result a higher number and a higher frequency. I will now show you this using some real numbers. So here we have our equation, 4 plus 0 divided by 3 something to 1, all multiplied by 2. If we put a plus here, we can see that it will equal 4 over 4 divided by 2. Multiplied by 2. This would obviously equal 2. However, if we put a minus in here, 4, that does not look like a minus, 4 over 2, all multiplied by 2, which would be 4. Now that we know what we know, we can apply this to some real life, completely realistic situations. So we have here a screaming child scurries towards a stationary observer at 25.0 meters per second. The frequency of the scream coming from the child is 800 Hz. The speed of sound is 342 meters per second. A. Calculate the frequency detected by the observer as the child approaches. B. Determine the frequency detected after it passes. So first things first, we're going to want to write down our givens. So velocity of the observer, 0 meters per second. Stationary means the same thing. Velocity of the source, 25.0 meters per second, right here. Velocity of sound, given right here, 342 meters per second. And the actual frequency, right here. Now, after we've written our givens, we should write the equation. F observed equals v sound plus velocity of the observer divided by v sound plus or minus velocity of the source, all multiplied by the frequency. We plug in our numbers into our equation. Now that's just juicy looking. 342 plus 0, since we know over here stationary observer, not moving, divided by 342. And since over here it's towards, we know that it should be negative or minus the velocity of the source, so minus 25 here, all multiplied by 800. Bring our math, not like that, bring our math up here. So 342 divided by, I'm not doing that in my head, minus 25 equals 317. Who would have known? 317 all times 800. So 342 divided by 317, a little over 1, times 800 equals, wow, beautiful looking, 863 point, what was that? 0.1 hertz. So for B, we have to do pretty much the same thing. Plus 0 divided by 342. However, now since it's going away from us, we do plus 25. So multiplied by 800, of course. 342 divided by 367 times 800. Now let's do that real quick. 342 divided by 367 equals, alright, times 800. 745.5. Units are hertz. The Mach number is defined as Mach number is equal to the airspeed of the object over the local sound speed. But in short, it's just a unit of speed of sound. So Mach 1 would be 343 meters per second, then Mach 2 would be 686 meters per second, and so on. If you have ever seen a certain Kevin run, he breaks speeds of around Mach 6, maybe even 7. Supersonic speeds are simply a rate of travel of an object that exceeds the speed of sound. Here's an example of a jet breaking the sound barrier, traveling at Mach 1. Now you might be thinking, well, what's the point of all this? Why does anyone care about the Doppler effect? It's only something you can hear in specific conditions. But I beg to differ. For starters, police use the Doppler effect to send sound waves with their radar gun to detect how fast another vehicle is going. Furthermore, spectroscopicists, which are pretty much a type of light scientist, use the Doppler effect when stars are moving very fast towards or away from us, just like the car and the screaming child were. They receive blue or red shifted light with different frequencies because, remember grade 10 optics, different colors have different frequencies. And then the light is discretized using quantum physics, which can then lead to determining the materials that the planet or star is made out of, and so on. These are just two quick examples of the vast uses of Doppler effect, and who knows, maybe someday you'll enter a field which relies on, or at least uses the Doppler effect in some way. However, that's the end of this video, and I hope you learned something or got your memory refreshed at the least.